Assalamu alaikum. In this video on optical fiber, we will see that what is optical fiber and what are the goods and bads of optical fiber. Because I feel that a lot of people now they have heard this name optical fiber, but mostly people they don't have very good idea. So this I have made these videos to help you to understand what is optical fiber. As an introduction, my name is Abdul Aziz Khan. I am a telecom engineer and I have more than 20 years of experience of designing and implementing telecom networks, and I have good knowledge of optical fiber networks. I have implemented some networks in Pakistan and Gulf, and I hope if you have any question you can email me your questions if you need any further after this whole video. So let's go ahead, inshallah. Basically, this will be consistent on 3 videos. I will make 3 videos. This is the first one on light and glass. In this video, I will tell you that because optical fiber is basically a fiber of glass and we pass light through it. So it's a combination of light and glass. So I will tell you that what kind of glass we use and what kind of light we use. This second one is more on optical fiber physical characteristics, and it's you can say technical nature, that what is the physical things and how we make and how we use optical fiber. The third video will be on the technology, what kind of technology are being implemented on optical fiber networks. So let's start. I will start with this very simple and very known example. I hope most of you have seen this decoration piece. I have seen it a lot in India, Pakistan and Gulf areas. People put it at home because it looks very beautiful. So if you see it, it has a small light source in this vase, and from this central point a lot of fibers are coming out, and you can see that at the end of each fiber strand you can see a small light. So basically the light inside travels through this small fiber and you can see this light from this end. Light is basically, there is no light here, light is inside, but that light travels through the fiber and it's coming out from the other end. So optical fiber is exactly the same kind of thing. You send a light source, you put a light source on one end, and that light travels from the fiber and it reaches on the other end. The only two difference between this decoration piece and a normal fiber is, number one, the fiber length is very high in telecom networks. You can have a fiber of 6,000, 8,000 miles. You can travel thousands of miles on that fiber. And the other thing is that this light that you can see here, this is a visible light. It is a normal light, a bulb light. But in optical fiber networks, the light is not visible. So it's in the invisible spectrum. So let's go and deep further. First, I should talk about the glass. That what kind of glass we use. Basically, the glass that we all are normally aware of is the glass in the window. The window glass has a very high purity for us, maybe because we can see on the other side. But if we put a light on one side and that light comes out from the other side, and if you have a 1 inch of glass in between, then in only this 1 inch of traveling, the light loses half of its power. So you need half of the power is consumed just to pass through 1 inch of a glass of a normal window. But in contrast, if you use a optical quality glass, the glass that you use in sunglasses or in the normal glasses that you use to read or whatever, because those glasses are very much high quality than the window glass. But still, if you have an optical quality glass of 10 feet length and you put a light on one side, then the light which will come out from the other side, it will have lost half of its power. So half of the power will be required to travel 10 feet in this case, whereas in window glass only 1 inch of glass was enough to reduce the power by half. And now we come to the optical fiber, the fiber optics. So as you can read it, this is very right, that in order for the light to travel and spend half of its power, it has to travel through a glass strand of 17.5 kilometers. However, this example is using the best quality, the ultra low loss fiber. However, but a normal fiber also, which is, you can say, almost double attenuation than this, still you can travel 9 kilometers and you will lose only half of the power. So you can see here, I mean, 18 kilometers in half power, 3 meters in half power, and only 3 centimeters. So you can understand that what kind of quality and what kind of purity we are talking about. So this is very highly pure glass, and this glass, we pull strands from this glass, and these strands are thinner than a normal person's hair. It's very thin, and the light travels through this glass, and we can travel thousands of miles distance through the optical fiber network. So let's talk about the light which is passing through this glass. Basically, we have three main portions in light. The first is called the ultraviolet. You should have heard about ultraviolet rays because these are used in our normal water purification systems as well. Ultraviolet can kill germs very easily, so it's a bit harmful for the human as well. If you put it on your body, I mean, if you are exposed to it, it can cause skin cancer. So you can say it's a bit harmful light. And then we have visible light. Visible light starts from violet and then blue and green, yellow, red, and then you have this infrared region. So you go from ultraviolet to the infrared. This infrared is being used in the optical fiber networks. So this infrared, the wavelength of the light is, you can say, lower here, and it's getting high and high. So infrared starts from almost 850 nanometers. The 850 nanometer light, even though it is used in telecom network and it's called invisible, but it's not fully invisible. It has some red color. You can see this light, I mean, if you try, but it's not good to watch infrared, because if it is very high power, then it can damage your eyes. So it works almost like lasers, I mean, so if you see into it, it can damage the cornea of your eyes. So but after 850 nanometer, we use 1310, and then we use 1550. So why we use these different wavelengths have their own, you can say, characteristics, and inshallah we will discuss it in later videos. The mostly used nowadays is the 1550 nanometer for long haul, for going very far, because this has the lowest attenuation. And within cities we generally use 1310 because it has some attenuation, lower than 1550 but better than 850. 850 is used within a room or within a building. It is not used for very long distance because the attenuation is very high. So let's see these attenuations. These are called optical windows basically. Like 850 is called an optical window. If you can see it, there is a dip in attenuation at this point, 850 point, and similarly we have a dip here and we have a dip here. And because this dip is the lowest dip, you have the lowest loss at this wavelength. So this is used more in very long haul systems. This is used in normal within city systems, and this is used within buildings. Also, we have an optical amplifier which is called EDFA. This is an amplifier which can amplify light in the light format. I mean, light will remain light and it will amplify it. Otherwise, generally, if you want to amplify any light, first you have to make the light, you have to convert it to some electrical signals, then you amplify those electrical signals, and then you have to put it on light again. So EDFA can amplify the light without changing it from optical to electrical and from electrical to optical. But it is most of it is available in 1550, so that's why we use 1550 in the long haul networks. Now let's discuss some of the problems that we sometimes get when we are sending light from one place to the other. So these are some transmission anomalies. The first one is attenuation, that we discussed earlier as well, that as you pass through a optical fiber, your power decreases with the distance. So this is called attenuation, your power decreases with the distance. The second thing we have is called dispersion. Dispersion is the spreading of light. When you pass through the optical fiber, your light starts spreading. Generally, this spreading is good because it's also it's a inherent criteria of light. I mean, light disperses by nature. Light should start dispersing, and that's why you put a bulb at one place and the light goes everywhere. Otherwise, your bulb should be giving you a ray of light, then it should not be of any use to you. So dispersion is in a way good, but in the optical fiber, dispersion is not what we need. I mean, we need light to stay. We don't want it to go out. The third thing is called non-linearity. Non-linearities are fiber characteristics. If a fiber has some non-linearity, then that fiber is not good for us. So some fibers has inherently non-linear, and they have non-linear issues like something we call like four-wave mixing. For example, if you are sending four sources from here, then you will not find four, may find 5 or 6 sources. So those four sources, they will mix with each other and they will produce one more source. So it will make a problem on your network, because you are sending 4 signals from here but you are receiving 5 or 6. So non-linearity is not good for us. So if we have a fiber with non-linearity, then we generally use it within the limits so that we don't go in the non-linear area. Distortion is any kind of problem that a fiber may have suddenly because of any reason. I mean, sometimes in a fiber on some particular place we start having a very high attenuation for no big reason. So, or maybe some other kind of issue. Sometimes the shape starts spreading for no good reason. So distortions are not good for us. And generally, if we have distortion on a fiber, then there may be some physical reason, and we have to correct that physical reason to remove those distortions. So generally, if you send this kind of waveform from one side, like for example, we send this light from here, so at the time of sending, you can see that the light waveform is very strong. I mean, light is this waveform is, you can say, very synchronized, and it looks that okay, everything looks fine. I mean, it looks very crisp and clear. But when it transmits a long distance like 1000 kilometers, this waveform starts spreading. Everything starts to spread. It can spread so much that maybe at some times you are not able to see anything. It all becomes one. So then it becomes almost impossible to separate the signals and to know that what was initially coming from this light. So whenever we are sending light from one place to another, we try to recover it in the best possible waveform so that the receiver at this side can understand what is coming to it. So whatever we were discussed, I mean, we will give a small description, like for example, attenuation. Attenuation is the reduction in the impulse amplitude, reduction in power. So for example, this is a fiber of 80 kilometers, and this fiber has a attenuation of 0.25 dB per kilometer. So it means that this fiber will induce a loss of 20 dB. So if we send 10 dBm of power from one side, we will receive minus 10 dBm. 20 dB will be reduced by this fiber. We use dBm in optical signals because dBms are very easy to add and subtract, because power is in dBm and the loss that you receive, the attenuation to receive, is in dB. So you can just add or subtract dB from dBm and dBm from dB. So it gives you very easiness in calculations. And this dBm, like for example 0 dBm is 1 milliwatt. So and minus 3 dBm is half of it. I mean, it's 500 microwatt. So dBm is basically a unit of optical power. And if you convert it to normal power, then 0 dBm becomes 1 milliwatt of power. Now we should discuss dispersion, the second thing that we saw. Dispersion is, as I told you, dispersion is that the light disperses or light spreads. So for example, if you are sending some light from one point, then on the receiving side this light disperses, and the wave basically spreads to the sides on both sides. So for example, if you are sending the wave, now the received wave should be taking more place on your spectrum. So if you are sending multiple sources, for example, if you are sending two waves from here, then those two waves can mix with each other, and on the receiving side you may start having some problem in understanding that from where one source start and from where one source end and then the other source start. So dispersion or this spreading can cause you some problems in transmission. The second kind of dispersion is called polarization mode dispersion, because light also travels in two modes. There are two polarization of light. So when you send the light on an optical fiber, those two modes, they can also disperse. I mean, they can also spread from each other. So this spreading can also cause the same kind of problems that if you are sending two or three or four sources, two, three waves, then they can mix with each other. But the good thing in chromatic dispersion is that we can, there is a solution. I mean, we can recover from chromatic dispersion. We can make the wave limit again. We can make it within its own limits. We can remove this dispersion. But the polarization mode dispersion is not easy to be removed. So in this case, we have to remain in the limit of the fiber. For example, whatever limits the fiber puts on us, we have to remain within these limits. We cannot go beyond the limits. So here are the you can say here are the pictorial representation of these problems. For example, attenuation. If you send a light pulse with this much power, so when it is received, the power is reduced. Now this wave is smaller than this wave, so this wave has less power. So this is the case of attenuation. In case of distortion or dispersion, if you have shape distortion and if you are sending a light here, this light spreads. Now you have the shape which is taking more space. One more thing that we can get in fiber transmission is that if you send some pulses, then the pulse can have some delays, and this delay is basically frequency dependent. So, and there are some other reasons as well. So it may happen that you send some samples on some specific time, but they are not received on the same time. I mean, so if this shape is a bit more delayed, then you will start missing the shape and you will start missing some data. You will start having data errors. So let's see how we can recover from these. So for example, if you have a attenuation problem, you are sending some fiber and the fiber is getting attenuated, then you can amplify the attenuated signal and you can bring it in the power shape again. The shape with respect to power can be corrected and you can increase the power again. So you will get almost the same shape. So if you have attenuation, you can amplify the fiber, the light, so you get the solution to the attenuation problem. If you are having a problem of shape distortion like spreading, or what we called polarization mode dispersion, if you have dispersion, then we have this DCU, it's called dispersion compensation unit. I will go in detail of these things inshallah in my next videos. But if you have a shape, out of shape fiber which has spread a lot, then this dispersion compensation can make it again within the shape. I mean, it can remove this spread and it can make it almost like the initial shape. And if you have a timing problem, I mean you are sending a pulse and the pulse is getting delayed in time, then what you have to do is that you have to regenerate. I mean you have to convert it from optical to electrical, and then you can retime the signals, and then you put it again on the optical, so you can realign the timing of the transmission. So I hope this video should be beneficial for you. If you have any question, please comment on the video, and please subscribe to my channel if so that you can start watching my new and old videos. I have put a lot other videos as well, and do contact me if you have any question regarding optical or other telecom things. I will be happy to answer you, and hopefully see you in my some next video. Assalamu alaikum.